All right, I think we've gotten started here. Okay, good morning, everyone. I hope some of you had a chance to take a look at those, try those two proofs for odd and even numbers that we left for last week. Usually I don't forget to put the answers to previous week's questions completely, as I did this week. So I just threw it quick and dirty into the actual second email. Generally, what I'll do is first of all, there'll be usually more problems, as this week is a good evidence of. I'll usually put them into, another PowerPoint presentation, a ghost version of where it came from with the solutions, and that'll be attached in the Tuesday email. So this first one on Tuesday was very unorthodox, so just throwing it into the text of the message itself. I'll explain that better next Tuesday when I'm showing you my solutions to the many problems that I'm be leaving with you today, leaving you with lots of homework problems to try if you're so disposed. Okay, so today is kind of like our test day to see just where we stand, where each of you stand in terms of solving simple equations, how much of you can bring back the algebra of long ago. And here on slide 1 is just a typical example of a linear equation. It's linear because there are no terms higher than, the power of 1. There are no squares and cubes, radicals, and things like that. The equations just have simple unknowns. That's like, for example, the x's here. But we can have all kinds of other things going on in a linear equation. As you can see, there are many terms. There's terms on both sides of the equal sign. There's brackets. We can both be throwing in fractions. They're all perfectly legitimate linear equations because they do satisfy the rule that the unknown term is only raised to the first power. And here's just a typical kind of solution just pulled off the web of one of the many places where you can review your algebra, many courses, many online worksheets and such that are out there of solving an equation with various steps. So it's something, if this looks very familiar to you as you go down one step at a time and you're nodding and saying, yeah, it looks right to me, then this class doesn't have too much to offer you because you're already at the place that I would like you to be. But if not, then I'd like to go through these kinds of steps and to review these are solution steps that we follow to solve an equation. Here are a bunch of examples down below in the lower right-hand corner of some more examples to try, which I actually asked you to try at some point here as exercises. Okay, so just to get us started, if you'll humor me, we'll demonstrate a magic trick that no matter what number you start with these various machinations of adding and subtracting and multiplying and dividing, will always end up with the number 3. So here I've started with the number 7. If you could just jot down a piece of paper, humor me if you would, jot down some number other than 7, a simple integer other than 7, and play along with me. So let's add 5 to our number. For me, I would get 12, and then double that to 24. Subtract 4 from your number brings me down to 20. Take half of that, which gets me to 10. And then I subtract the number that I started with, which was 7. And lo and behold, by magic, I come up with my predicted number of 3. Okay. And this is what's going on, of course. Instead of picking the number 7, I picked the number pi. And I did all those various machinations. I added 5 to pi, and then I doubled pi by multiplying 2 times that new number, pi plus 5, getting 2 pi plus 10, and et cetera, et cetera. And sure enough, the next to last number that I had here is pi plus 3. And so when I subtract the number I started with, pi, I wind up with the number 3. Okay. Another one. No matter what number you start with, you'll always end up with that number, the number that you started with. It's kind of even more general. Here, the first one, I was always giving you 3. Now I'm going to give you back whatever number you started with. All right. Humor me, guys, and play along and write down a number other than 5, some simple integer. And we'll triple it to get 15, and then we'll increase that by 1 more than the original number. Okay, so 1 more than 5 is 6, brings us up to 21. We'll add 11. We'll divide that 32 by 4 to get 8. And then if we subtract 3, by magic, we come back to our original number of 5. Okay. And here, instead of being cute and using pi as a placeholder, let's actually just use any number x. And of course, x does not have to be an integer. That's the reason why I chose pi. Okay, to tell us that these are not just integers. This is any number you would like to use. And we go ahead and triple that number to 3x, add 1 more than it's the original number. The original number is x, so 1 more is x plus 1. We add that to the 3x. We add 11. The 1 becomes a 12, divisible by 4. Important here to recognize that 4 is over both terms, right, of the expression. It's over the 4x and over the 12. The silly mistake there is if you're going to cancel out and simplify, you just simply divide the 4 by the 4x and you leave the 12 alone. No, 4x plus 12, that entire expression is over 4. And both sides, everything in the expression must be divided by 4. So we do that and get x plus 3. And then we subtract the famous 3, and lo and behold, we're left with the number that you started with, whatever that is. Okay, so just a little demonstration of algebra, right? And how these things are done, seeing that we're just moving in different kinds of circles using these algebraic manipulations. So one more trick, I promise. That is to duplicate any 3-digit number. Here again, I want to kind of look at the structure, the skeleton of what the place value is, to remind us of that. We kind of ran through it very quickly at the end of last week. Take any 3-digit number. I have 358. Multiply it by 7, then multiply that by 11, and then multiply that by 13. And the 358 becomes 358, 358. It becomes 358,358. And this will be true no matter what number you start with. So if we start with x and multiply by 7, and then multiply that by 11, it gives us 77x, and then multiply the 77x by 13, and there's the secret of the trick, right? 13 times 11 times 7 is 1,001. And 1,001 times 358 will indeed give you 358. And in fact, 1,001 times any 3-digit number will simply duplicate those 3 digits. So I'd like to just demonstrate that to highlight, remind us of the place value, what a number means. 247, I picked a different number than 358 just to show it doesn't matter what number you pick. 247 times 1,001, I can say certainly that 1,001 is 1,000 plus 1. And then I can use the distributive law and multiply the 247 times 1,000, 247 times 1, and sure enough, we'll get 247. And finally, if we look at this in its skeletal form using place value, I write the 247 as 2 times 100 plus 4 times 10 plus 7 times 1, 1,001 written in the same way. And then when I multiply the 1,001 times 247, I have that 1,001 as 1 times 10 to the 3 plus 1, 1,001. My skeleton version of 247. And again, I use the distributive law. First of all, multiplying the 1,000 through, then multiplying the 1 through. And the point I want to make here is that multiplying 10 to the 3 times 10 to the 2 is 10 to the 5. 10 to the 3 times 10 to the 1 is 10 to the 4. I'm adding exponents. That gives me my first number in the thousands. And then 1 times anything leaves everything else alone. And finally, when you look at the final product of 2 times 10 to the 5th plus 4 times 10 to the 4th plus 7 times 10 to the 3rd plus 2 times, etc., that is exactly the meaning of 247, 247. Okay. So again, just to remind you again of what we mean by place value and its importance, and also to kind of demonstrate the law of exponents. That what is a cubed times a squared? Well, it's 3a's times 2a's, right? A cubed is a times a times a. But clearly a cubed times a squared is, there are 3 of them times 2 of them. Put them all together and you get 5 of them, and then we see the law. A cubed times a squared clearly is a to the 5th, and that's 3 plus 2. So there is our law of exponents, which is what I was using here over on the left side. Okay, I just got my message, your internet is unstable. I hope I'm not breaking up too much. I wonder if
Just
Jenny is
now
here.
and then.
Is Jenny here this morning?
Yep, you're breaking up a little bit now and then, but
Okay. Again, as Jenny suggested last week, if you could turn off your videos, that seemed to have helped. If Jenny, if this continues, if it gets bad, I'll turn off my video so that there's one less signal having to go back to you guys. I'd rather not do that if I don't have to, but let's do that if the sound really starts to become bad.
okay.
All right. So let's get to the agenda of today of solving linear equations. The idea of solving equations is simply to write down a series of equivalent equations until you get the one that says x equals something, that x is on one side and everything else, whatever it may be, whatever it may turn out to be, what the algebra tells us it must be, is all on the other side. We consider that a solution to the equation if x is considered the unknown. That's the game here, okay? And the game is to write down literally a series of equivalent equations until the last one is the one that you want. So let's just look at that quickly. Here is, I claim, is an equivalent equation to the one up on top. Take a look at what I've done there in that second equation. I claim that I've used legitimate rules to make that second equation be exactly the same as the first one. Another simplification that I've done, notice the only change from the second to the third is a negative 8x has appeared. The rest of it has not changed at all. Big simplification, here I'm well on the way. Remember, the idea is to get x on one side, just one x, and everything else on the other. So I've got 14x on one side and everything else on the other. It seems like I'm almost there. And then finally, I do isolate x by itself, which I claim, the final answer, the solution would be x is equal to 1/2. Okay, so what have I done? Well, that first step, I eliminated the parentheses by using the distributive law. Sure, I multiplied the -2 through and I multiplied the 5 through. In the second thing, that -8x appeared because I collected like terms on each side. There are no like terms on the left side. There's a number term and an unknown term. They're not like terms, so there's nothing to combine there. But the -5x and the -3x certainly can be combined. I isolated the unknown term on one side. This, I guess, is the key. This is the big deal. This is where the word algebra comes from the Persian. It actually means to rebalance, to reset. It was used in the same way by bone setters back in the day before there were doctors who were doing that, and that's where this word comes from. And so this is the resetting. We're rebalancing the equation where all the x terms are on one side and all of the non-x terms are on the other side. Okay. So I've done something to make that happen. The something is to add opposites of some of the terms to both sides. And then finally, to isolate x by itself is, I claim, is a multiplication process, multiplying through by the appropriate inverse. Here, the inverse that I'd be looking for would be the inverse of 14. Okay. So eliminating parentheses, well, again, multiplying the -2 through and the 5 through. Collecting the like terms, there's where the -5x and the -3x becomes -8x. The isolating the x term on one side. Here, I'm just trying to get rid of the -8x on the right side. What happens to the left side will happen to the left side, but whatever I do to the right side, I must do to the left side. Otherwise, I destroy the equality, I destroy the equivalence. My goal here is to get rid of the x's on the right side. That's why I'm adding the 8x. I choose the 8x because I want to get rid of the -8x on the right side. In doing it to both sides, I get whatever I get on the left side. I can't control that, but I can control the fact that I have no x's on the right side anymore once I do that. For exactly the same reason, I added 2 to both sides, because I want to get rid of the number term on the left side. Doing it to both sides, whatever happens on the right side will happen on the right side by properly adding 2. This leaves me with the 14x is equal to 7, and now finally is to eliminate the 14. Well, you just don't eliminate it, you've got to do something with it. And multiplying the entire equation, just as I added a +2 to both sides, I added a +2 to the entire equation, keeping both sides. I'm now going to multiply through by 1/14. All the terms of the equation get multiplied through by 1/14. And 1/14 times 14x is x, and 1/14 times 7, which is, of course, 7/1, is 7/14. Simplified to 1/2. And there it is, guys. There's what you used to do long, long ago.
Peter?
Yes, question?
Yep. In the last step, why do you multiply by the inverse rather than simply saying divide?
Okay, very good question. We, of course, will revert to the algorithm of dividing both sides by 14. They are equivalent. I'll make that point in a little while, that dividing by 14 is the same thing as multiplying by 1/14. Okay, it seems like it's an added complication. Why don't I just simply say, instead of saying multiply by 1/14, equivalently, it is to divide by 14, which is exactly how we think of what we're doing to both sides. They are exactly the same. I'm trying to make the point because as we get into more complex situations, it is important to realize that all division is multiplying by the inverse. And I'll try to make the point of why that is important in a few slides. But absolutely, the algorithm for the last step is simply to divide both sides by 14. Absolutely. Okay, the famous check, where we check what we're doing. And here I claim the solution is 1/2. And so the idea is to substitute 1/2 every place in the original equation for x. So I have 3 x's, an x term here, 1 here, and 1 here. And I substitute 1/2 into each of those places. And here, if you want to review your fraction manipulation, there are many, many ways of simplifying this expression. But if you do want to simplify this, this expression, getting rid of all these fractions, this would be a good little test that you're up to speed on fooling around and clearing out these fractions. There's a second one coming up. This one is relatively easy. I want to look at the second one more carefully, so we'll skip the check here. But ultimately, what you're looking for is an identity at the end. Here, I show that 1 is equal to 1. I can stop there. That's the check. If anything will do, 5 is equal to 5. Any identity will do for the check. So I'd like you to solve the equations from slide 1. Those examples down below, and I gave that as one of the pages of the first handout sheet. I'll providing solutions. My solution, first of all, I provide the solution on the question sheet itself, right? Those are in the square brackets. And I'll provide the full worked out solution next Tuesday. Okay, let's try one where we're going to contain fractions. Here I have an equation that has a denominator on one side of 3, and I've got a fraction of 3/2 on the other side. Important to realize that that is not 3 over 2 minus x. If I wanted to mean that, I'd have to put 2 minus x in a bracket so that 3 is over the entire expression, 2 minus x. That's not what this says. The 3 is only over the 2, not over the minus x. There are 2 separate terms on the right-hand side. Okay. Again, a series of equivalent equations. This one may be a little mysterious as to how I've done this, but I have done a good thing. I've gotten rid of the fractions. The fractions are now gone and everything is along one line. So whatever I did was a good thing, because here we can proceed pretty straightforwardly like the other one, clearing out brackets, isolating the different terms on each side, and clearing through by the division on both sides. Okay, so it's that first equivalence may be a little strange how I got rid of the fractions. The trick is to eliminate the denominators by multiplying through by a common denominator. The one that I used here was 6. Notice it's a common denominator, not necessarily the least is great. By all means, use the least common denominator, but any common denominator will do to do this. We'll just have to reduce things to lowest terms as you work through if you're not using the least common denominator. So that's the trick there, is to I multiplied all 3 terms, 1 term on the right side, on the left side, and 2 separate terms on the right side. I multiplied each one of those terms by 6, because I claim by doing that, I will eliminate all of the fractional elements of those terms. I'll get rid of the denominators. And then following our nose, we'll eliminate the parentheses, collect like terms, which is already done. All the like terms are collected on each side. And doing the balancing act and finishing off by dividing by 8. Okay, so that first manipulation we can look at a bit more carefully. I'm multiplying the entire equation by 6. And that's the reason why I wanted to show you that when I'm going to multiply by 1 over 14 here down the very bottom, I'm again being stubborn. I'm going to multiply through by minus 1/8. I'm trying to emphasize that I'm multiplying through the entire equation, even though that bottom equation only has 2 terms. My process, my algebraic process, is I'm multiplying that outside term through, just like as if it were a bracket, even though there's an equal sign somewhere in the middle of the bracket. It makes no difference. And the reason why I'm showing that down the bottom for a while before we get to just dividing, because of this up here, the importance of multiplying through by a common denominator. To realize that whatever you decide to multiply through by, whether it's an inverse at the end or some expression earlier on, you must multiply through every single term of the equation. Otherwise, you will break the equivalence. And notice that 6 times that expression, x plus 5 over 3, is nothing more than 6 over 3 times the expression, which is nothing more than 2 times it. 6 times 3/2 is nothing more than 3 times 3, which is 9. And finally, 6 times negative x is a full negative 6x. Every single term gets multiplied by 6, not just the ones that have the denominators. Otherwise, you'd break the equivalence. You haven't done the same thing to every single term. So that's the purpose why I picked this equation, to try to point out some of these old rules from the past. The rest pretty much is following our nose as we have done previously. Again, the balancing, wanting to get rid of the x's on the right-hand side, I choose to add a plus 6x to both sides. Wanting to get rid of the 10 on the left-hand side, I choose to add a negative 10 to both sides. What I get when I do that, I have no control of the other side. Turns out that I get 8x on one side and I get a negative 1 on the other side. That's just by following my nose and doing the algebra properly. And then I'll give up here. I'll divide both sides by 8, okay? But I did write down the multiplying by 1/8, being stubborn. Okay, and so the answer is negative 1/8. And here, again, to check, now I'm substituting something a bit more interesting. First of all, it's a negative fraction, and it's not something as simple as 1/2 or 1/8. Let's just look at this. Again, humor me to look at the fraction manipulation here. I want to substitute negative 1/8 every place where I see an x on my original equation. There are two places where there are x's here. So here I get a negative 1/8 here, and I put in a negative 1/8 here. Did nothing else, just made the substitution. Okay. Like to do something here, like to add these two fractions. Oh yeah, 5 is a fraction, it's 5/1. So if I want to add these two fractions, again, not using our algorithm yet, by turning 5 into 8ths, we've got 48ths, and so there's a negative 1/8 and a 48ths. I'm able to handle that. And here, a minus times a minus is a plus. You know, one simplification at a time here for now. So I got rid of that double minus. All right. So minus 1/8 and a 48th is 39/8. Didn't change the 3 down the bottom. I want to add two fractions, 3/2 and 1/8. I need to change that 3/2 into 8ths. Then I can add up 8ths to get 13/8. My next simplification is, yeah, although this is an equation in numbers, it's still an equation, and I can do any valid equation manipulation. Here, I chose to get rid of this denominator 3 by multiplying the entire equation through by 3. It's exactly the same idea. I'll get rid of that 3 because 3 times 39/8 over 3 is 3/3 times 39/8, which leaves me with 39/8. And 3/1 times 13/8 is 39/8. And I have an identity, and I can stop.
Peter?
Okay, yes, question?
Problem 5 on the first page. Someone said they got a different solution, and so did I, plus
Okay,
6.
thank you. Thank you. Very good catch. Let's take a look at that. Let me just finish my slide here.
Okay.
And let's very much take a look at that. I failed to say that. I wanted to say that in the introduction. Please check my work. I am not infallible. I try to be careful, but as we all know, we're all prone to silly mistakes. And I do appreciate you catching mine. It's the first one. I promise you, it won't be the last. But I will endeavor very hard to minimize my mistakes. But let me just finish my thought here on fractions. So what is A over B? Well, you can think of it as a fraction. You can also think of it as a division. It's B divided into A. Whatever A and B are, they can be numbers. They can be vast algebraic expressions in themselves. But whatever they are, you can think of that as dividing B into A. Certainly, you'll agree with me that that's equal to A over 1 times 1 over B, because if I multiply through the tops and the bottoms, I will get back A over B. So that is true. So we can see that dividing by B, or something over B, is in fact the same thing as multiplying the number by the inverse, okay? And that was the point that I was trying to make. So dividing by B means to multiply by the inverse of B. And that's why I was being so stubborn before. And I think I'll continue for a while in these later slides, where I continue to be multiplying through by inverses, trying to hammer home the point of that equivalence. Here we have a fraction over divided by a number, C. Again, these can be very big expressions, but now I claim that Dividing by c is the same thing as multiplying by the inverse. The inverse of c is 1 over c, and multiplying across, I get a over bc. And there's an algorithm that I want to remind you of. When you have a compound fraction like that, the algorithm is simply to move the c underneath with the b, and it simply becomes a over bc. Okay, there's a reason. The reason is right there. The reason is the middle term. That's why the algorithm is true. But certainly, you know, we want to be able to use our algorithms intelligently, and there's something that we'll be doing all the time, as it turns out, simplifying you know, these double-decker fractions like this by combining in the proper denominator. An example from the left-hand side, that 39 over 8 over 3, I got rid of it by multiplying the whole equation through by 3, remember? Yeah, I just could have went ahead and used the algorithm, and that's 39 over 8 times 3, which is 39 over 24, which we can simplify by reducing lowest terms. And the ultimate of it all, a fraction over a fraction. Well, I claim that dividing by a fraction is the same as to multiply by the inverse. The inverse of c over d is d over c. And so dividing by c over d is the same as multiplying by d over c. Multiplying across gives us ad over bc. Okay. The algorithm to divide by a fraction, invert and multiply. That phrase should be somewhere rattling around in your head. You've heard it a million times. To divide by a fraction, invert the denominator and multiply. Okay. An example, 3x over 2 divided by 9 over 4 is the same as multiplying by 4 over 9. Multiplying across the numerators and the denominators, reducing to lowest terms, we get 2x over 3. Okay, we come to the handout, which apparently I've done something wrong. And again, I appreciate you catching that. I'm going to grab my hard copy of this, so I know what I'm doing here. Forgive me to okay, I think I've got my hard copy of what we're working with. Let me close this thing down and find where we are. Is it in these equations here? Are these the equations that we're talking about, guys? These guys down here, or the second sheet?
It's the sheet that you sent with, that has
Okay.
2 pages.
Okay, so I
problems on each.
don't have that sheet here in the PowerPoint. All right. So which I've got the sheet in front of me. If you guys could, if you hopefully maybe you've printed out a hard copy, if you have this.
It's number 5.
5 times y minus 6 is equal to 2 times 6 plus y. Have
Yes,
I got
that's
that the right equation that we're talking about?
Yes.
Okay, I claim that y is equal to 6. All right, let's see what I've done wrong here. I multiplied through by the 5 and got 5y minus 30. That seems okay. And multiplied 2 through that bracket and got 12 plus 2y. Okay, so far so good. Using our algorithm, I brought the 2y to the other side, right, and got 5y minus 2y is 3y. And then brought the 30 over to the other side, isolating the y's over, making that into a plus 30, and 30 plus 12 is 42. So far, so good?
Yes.
Okay, dividing everything by 3, 3 into 42 is 14. Is that wrong?
Well, you have y equals 6.
Yeah, 14 is correct. You have 6 written down.
Oh, my goodness. Oh, my goodness. Okay, so my solution is right. My hint answer is wrong. That's, oh, guys, that's really neat, sneaky. I mean, that talk about low-handed, giving you a hint and being the wrong hint. Ay, ay, ay. I really
six as
apologize.
well.
I really apologize for that. I will, clearly I need to check, you get a little blurry out and you put these things together. Clearly I must check before I send this stuff out. What a silly mistake. Here I have the solution down below and the hint I left is 6. All right. Thank you very much. Ay, ay, ay. All right. That's just sinister of me.
6 as well. Did you hear that, Peter?
What's that?
Number 6 is also, I mean, it doesn't even have the same variable there. You have a b in the equation and then an x equals 3/7.
Yeah, and the answer is not 3/7.
No.
I must have, I did a lot of these problems. I pulled a lot of them and I did a lot of them to try to find ones that I thought would bring out some kind of a point I was trying to make. And what this shows me, guys, is I did not do a good job in straightening this out and clearing out the stuff that I wasn't going to use from the stuff that I was going to use. This tells me I must do a better job being more careful in preparing the final sheets for you guys. So I really do apologize for this. This is kind of unforgivable to do this. All right, yes, the answer is, as my solution shows here, my answer is b is equal to 6. Is that correct? You guys agree?
Yes. Yes.
Right. What I was, where 3/7 comes from was some problem that I must have done someplace else. Oh,
It's actually
It's
the
a-
answer to number 6 on the second
it's,
page.
yeah, that's it, 6 and 6. Yeah, so I'm just being very sloppy and pulling these pages together. I've got equations all over my desk trying to pull ones which I feel are useful for us to look at. And when I think the final copies, I'm being very sloppy pulling it together. Let me apologize one more time and I will try to let that not happen again. All
No,
right, can we continue? Is this a good place to continue on?
I think so.
Where are we? I think we're here. Is this where we are?
I think so, Peter.
Okay, yeah, we finished the 2 equations and I just wanted to remind you of some geometry formulas because we'll use these in our word problems. These are standard kind of formulas that we should have at our disposal to handle some of the word problems. So looking at areas and perimeters of various geometric figures, the square, the rectangle, just don't need much explanation. The parallelogram and the rhombus, I actually will prove the area formulas in a moment. And the trapezoid is a nice formula for the area down the bottom of that first column. The trapezoid, the area of a trapezoid is the average of the bases, the 2 bases divided by 2 times the height. Interesting formula for the area of a trapezoid. The circle, of course, so important. The area of a circle of pi r squared, and the circumference being 2 pi r. The area of ellipse, where the ellipse is measured by a major axis and minor axis of a and b, is pi times ab. There's no simple formula for the perimeter of an ellipse. For a triangle, the very important formula, 1/2 the base times the height. All triangles have that. Formula for the area. For a right triangle, it's easy to see because you can make the 2 legs the base and the height if you like. For a triangle, which is not, you have to, basically create the height sometimes by choosing a vertex and dropping down a perpendicular down to the opposite side. No matter where it falls, you can extend that base as long as you like to realize the height. And that's what that picture is trying to show. And finally, for an equilateral triangle, you can actually write the equation for the area a little differently by just having it as depending upon the common side of b. The formula is radical 3/4 times b squared. And I thought that could use a little bit of explanation as well. And these are just examples where I can use some algebra. Just trying to find places where we can exercise and practice our algebra. Clearly, the perimeter of an equilateral triangle is simply the sum of well, it's always the sum of the 3 sides, but they're all the same, so it would be 3b. few other things to remind us of is 180 degrees in a triangle, Pythagorean theorem. Here it looks a little funny because I'm using this figure. So c squared is equal to h squared plus b squared. And the SSS congruence, when two triangles are congruent, if their three sides match up. If all three corresponding sides of two triangles are equal, then the triangles are congruent. They're identical in every way. They're simply two different triangles written in two different places. It's the same triangle written in two different places. So just to remind you of some fundamental stuff that we will be coming across. Okay, let's do a couple of proofs. The area of a parallelogram and a rhombus. I claim the area of a parallelogram is the base times the height. So the proof, let's draw a diagonal, and that creates two congruent triangles, 1 and 2. Yes, because we have AB and the diagonal and AB in the same diagonal. So we do have congruent triangles, and therefore if I can figure out the area of one, I just need to double it to get the area of the whole parallelogram. But notice that the area of each triangle is base times height over 2. And so each triangle has base times height over 2. So the area of the whole thing is twice that. And that would be the base times the height, which is what I claimed. The area of the rhombus of the two diagonals, P and Q, is half of their product, is what I claim. Again, the proof, the diagonal P again creates two congruent triangles for the same reason. We have AAP and AAP. So we have two congruent triangles, top and bottom. And pulling a theorem out of Euclid, the diagonal P actually cuts the diagonal Q in half and is perpendicular to it. Kind of pull that out of Euclid on you. So please take that on faith, that the diagonal P does divide Q in half. And now I can look at the area of the top triangle and the bottom triangle. The area of each triangle would be the base times the height times a half, but the height is a half of Q. So it's the base times a half of Q over 2. And isn't that funny? But there's where that double fraction comes in, where I can bring the 2 up into the other 2 and get 4. It's amazing how often this algorithm comes into use of having a fraction over either a single number over a whole fraction. Of course, that fraction Q over 2 is over a fraction because 2 is over 1. And if you invert and multiply, that becomes 1/2. And that's why the 1/2, that's why the 2 2's multiply. Again, the reason for the algorithm, not just the algorithm. And so doubling all of that gives us PQ over 2, as I claimed. And finally, using the Pythagorean theorem to get this little formula, I want to take 1/2 the height times the base. I need to realize the height. Another theorem from Euclid, that when you drop a height from an isosceles triangle, you get that height is perpendicular to the base and will bisect the base, using theorems from Euclid, which I imagine are familiar to most of you. And then I can find out what that height is by writing down the Pythagorean theorem, doing a standard algebraic manipulation of bringing the b over 2 squared to the other side and getting h squared. That's b squared minus b squared over 4, which is 4b squared over 4, minus b squared over 4, which is 3b squared over 4, and then taking the square root of both sides. Again, notice the writing here, this square root sign doesn't go very far. This is the one that I'm given for square root sign. So I have to use brackets to show that everything here is under the square root sign. Okay, that's what you have to show, that otherwise only the 3 would be under the square root sign. But I do have everything under the square root sign. And I can take the square root of that, and b squared certainly has a square root, and 4 has a square root. The 3 will remain under the square root sign. So now that I have h, I can apply my formula bh over 2. And again, I've got a compound fraction. Again, that b over 2 over 2. And the 2 b's will multiply up, but the radical 3 stays alone. And so the formula that I claimed. All right, let me just go through these 2 slides and then I'll see if there are any see if there are any questions if I'm going too fast. Literal equations are better known as formulas, where we have mostly letters, relationships between quantities. These I took from the geometry page. Here we have the area of a rectangle. Well, here the equation is solved for the area. I asked you to solve for the height, and solve really for any letter you like. And so here, solving for the height, I claim is A over B. The area of a square, solving for the side of the square, taking the square root of both sides. Here's one for you to try. There's that area of the rhombus. The next one is the area of a trapezoid, asking you to solve for B. B is kind of dug down in there inside. What I chose to do it was I multiplied through by the common denominator of 2, and got 2h, got 2a, and the 2 is now gone from that side. Instead of multiplying through by h, since I want to isolate b, why should I kind of muck up the waters by getting a bh, kind of defeating the purpose of getting b by itself? So let me just right away get rid of the h by dividing both sides by h, and that will just leave me with a simple a plus b term, and then I can simply subtract a from both sides. That's a perfectly good answer. This is a perfectly good answer, 2a over h minus a, but if I wanted to write that as one compound expression, that I would need to add fractions, common denominator of h, and using our algorithm, h into h goes 1, and 1 times 2a is 2a. 1 into h goes h times a is ah. And 2 other ones for you guys to try to unbury b from the equilateral area formula and unburying b from the primitive formula for a rectangle. And here are things which would be more worthy of you guys, taking some real equations from the real world, mostly from physics. I have a little explanation of each equation up on top, and asking you again to dig out, isolate from the equation certain of the variables. These are all in blue because I'm asking you to try these yourself, and I'll be providing answers to these next Tuesday. All right, Jenny, do we have any questions? Hello. Have I lost everybody?
No, Peter, you haven't lost everybody, but no questions at the moment.
Okay, all right. Jenny, can you hear me? I may have lost her. Okay. All right, thank you.
I can hear you, Peter,
Oh,
but
okay,
you do keep coming in and out again.
I do. Should
Peter?
I wonder, should I turn off my video?
We could try that.
Let's try that. Let me stop my video. That'll freeze me to the icon picture of my Google accounts.
Okay,
Okay, there's me frozen. Let's see if that helps.
all right.
All
Sounds
right.
good.
Peter,
Yes,
Peter, are you gonna send all these things out that you want us to try?
yes. Every problem that I give you, I will supply a solution.
No, I
Also-
didn't mean a solution. I meant, are you gonna send the problems to us on a sheet of paper? Or
Oh, No,
Spreadsheet.
the slides, I'll ask you just to kind of write
Go
down the
through the
equations
slides
from
and
the
find them.
slide yourself on a piece of paper.
okay,
Yeah, okay, yeah, thank you. All right. Here's an interesting question where we can practice our business of dividing a fraction by a fraction, just to make the point. We know that we are pulled by the earth. Any mass is pulled by earth according to the formula of the law of gravity. G times that mass times the mass of the attracting body over the distance between those two bodies. So I ask a question. The earth certainly is pulling us down, and the sun is pulling us up, right? And gravity works on every two bodies in the universe. So we're going to ask the question, clearly the Earth is pulling us down more strongly than the sun is pulling us up, otherwise we'd be floating up to the sun. And the question I pose is, how much stronger is the Earth pulling us down than the sun is pulling us up? And it's just an exercise to allow us to practice dividing a complex fraction by a complex fraction. Okay, an exercise. Exercises are important, right? Exercises are in every field of learning, right? All the field of sports, all the field of music. You do exercises, you know, for the purpose of strengthening certain pieces of manipulations that we'll be using over and over again in the real world. So I tried to put it in some kind of a context of that was real. All right, so we consider the mass, any mass that's on the surface of the Earth, like for example, your mass, and we would look at the, I think I went the wrong way. We look at the gravitational force that the Earth pulls down using our formula. Here we'll be using the mass of the Earth and the radius of the Earth, and the force that the sun would be pulling on us. Here we would use the mass of the sun and the distance that we are from the sun. Astronomers call it 1 AU, 1 astronomical unit, the distance from the Earth to the sun. So we would have the ratio of the two forces, the force of the Earth pulling at us down and the force of the sun pulling us up, in that sense, a ratio of one complex fraction over the other. And the whole point is to simplify that fraction by changing that into a multiplication. And I apologize, I have an error. This bracket, of course, should be, this bar should, of course, be gone. That is the whole point of inverting and multiplying. I no longer have a fraction over a fraction, but I have two multiplications. So I apologize, guys. This is wrong. Okay, it should be simply this fraction multiplied by this fraction, which is the inverted fraction of the first denominator. Okay, apologies. So there it is there. I think I got it right by multiplying across without that incorrect bar fraction line. Bringing everything into one numerator, bringing everything into one denominator. And the point is that G little m is on top and bottom, which is just one big one, can be canceled out. And we're left with that simplification, and can be made a bit more coherently by looking at the ratio of the masses and the ratios of the distances. But the ratio of the distances, of course, are square. And to put in some numbers, again, I wanted to just kind of practice a little bit with exponents. The mass of the Earth is 6 times 10 to the 24th kilograms, and the mass of the sun is much greater, 2 times 10 to the 30th. Okay, about 6 million times more, 3 million times more. And the distance, obviously, to the sun is much greater than the radius of the Earth. Here we have 10 to the 11th compared to 10, just 10 to the 6th. Those numbers are in meters. And I just wanted to show the simplification that 6 over 2 is 3. And how you handle the multiplication of exponents is to add them. Not surprisingly, how you handle the division of exponents is to subtract them. And that's really the purpose of finishing off with the arithmetic. Is 24 minus 30 is minus 6, and 11 minus 6 is 5. Okay, you can get your calculators out at this point and simplify. These are just numbers, and you get about 1800. So we are safe that the pull of the Earth is almost 2,000 times stronger than the pull of the sun on any given mass. Notice the masses, the individual mass that we were concerned about dropped out of the whole expression, that this ratio of forces is the same no matter what mass you're considering. All right, we want to start to go through some word problems quickly. Do we have any
Peter,
questions?
there's one other question.
Yes.
What are we to solve for in the literal equations? First it says to solve, but then it has it done.
Yeah, I think in some of the literal equations, I'm asking you to actually solve for two different letters. That is two different solutions, solving for one letter and then going back to the original equation and solving for a second letter. Is that clear what I'm saying?
Michael, is that clear to you now?
Yes.
It's actually two separate questions, trying to ask you to dig out two different variables from that original equation. Okay. Reason why we practice word problems is because we're interested in trying to learn, trying to review how we use algebra as a language. And these are the exercises that we start with, because here we literally are translating English sentences into algebraic equations. They're silly sounding, their jokes are made out of when you read these problems. They sound like, what? You know, who would ever? But they are, in fact, exercises to try to review and to learn and to become comfortable in turning ideas, as silly and as stilted as some of these ideas may seem, into mathematics. That's the point. Okay, so a number problem. Find the number. That's the whole point of these problems. 7 more than 3 times a number is 22. Going through them slowly. Here I did this, this Zoom kind of thing. This is very important to start off any word problem by saying, let the unknown be, you must identify your unknown. Otherwise, your whole translation breaks down, right? The equation will not be translatable unless you know what you're using, what is the idea that is being signified by the unknown. And if you have more than one unknown, you have to identify every single one. Otherwise, there's no translation process. It's all in your head. No one else can understand the language of algebra that you're using. Okay, so we all remember the let statement from our algebra. So if x is the number, then 3 times that number is 3x, and we're told that that sum is 22. Okay, and so I will not go through these solutions in detail, though I have them. Okay, and we can check, in fact, that 5 is the right answer, getting an identity of 22 is 22. We're really looking at the translation process. And here are now the word problem sheets that we have. Has anybody found a problem with any of the word problem sheets? No? Okay.
Well, I couldn't solve some of them, so I don't know.
I'll keep my fingers crossed on that score. An age problem. 7 years from now, John will be 3 times as old as he was 15 years ago. I agree, yeah, but it's practice in trying to tease this thing out and to translate it. How old is he now? If x equals his age now, 7 years from now, it'll be x plus 7. 15 years ago was x minus 15, and we're told 3 times that. 3 times x minus 15, well, that's the same as what he'll be 7 years from now. So there's the equality. That's the exercise, guys. That's what's interesting, to be able to do this comfortably. I'm assuming now that most of you, can, as the physicists like to say, the rest is just math. The rest is just following your nose, clearing out the brackets, doing the balancing, dividing both sides by 2, and getting the age now of 26. And that is true, because 7 years from now, he'll be 33. And that was true. That is true that 15 years ago, when he was 11, 3 times that is 33. Okay. Another age problem from the past, just to show that you need to have confidence in your answers, that the answers make sense, that the algebra will make sense to you as a language. John is 56 years old and his son is 29. In how many years will he be twice as old as his son? Well, let x equal the number of years that it'll take until John becomes twice as old as his son. That would be naively how we would begin this. Let x be the number that we're looking for, the number of years that we're looking for. So John will be x plus 56 plus x then, and the son will be 29 plus x then. And we want to find out for what x that 56 plus s is twice his son's age, 29 plus x. And what's interesting here is when you solve the equation, you get a negative number. And that is the correct answer. In fact, it happened 2 years ago from the present tense of how the problem is stated. 2 years ago, John was twice as old as his son, because if he's 56 now, he was 54 then. His son was 27 then, which he was twice as old. 54 was twice as old as the 27. So again, using algebra as a language, that -2 is an age in the past. It's real. It means something in the real world. Okay. We'll be doing quite a bit of study of motion problems, not just these simple ones where it's always distance is equal to speed times time. We'll get more elaborate, more interesting, but we'll start here with these motion problems. I have a lot of them, as you can see, because this is a theme that will work right through the calculus. As some of you know, motion is a great thing, a great problem that Newton was trying to solve, and which he developed the calculus, was to explain the motion, the complex motions that we see in the real world. This is part of where calculus comes from. So we'll be using motion problems, and they'll become more and more sophisticated. That's why it's seemingly the obsession of I have here with these motion problems. Two cars travel in opposite directions, leaving at the same
Peter?
time.
Peter,
Yes.
there's a request for you to go a little bit slower with these.
Okay. Thank you. Two
Yeah.
cars travel in opposite directions, leaving at the same time. Okay. One goes 35 miles per hour, the other 50. They are 255 miles apart when they stop. They're going in opposite directions, right? They're going at these two different speeds. And at some point, they're 255 miles apart. We'll stop the clock at some place. How long have they traveled? How long has it taken for them to get that kind of distance apart? Okay. The fundamental formula is up on top there, guys. Distance is equal to the constant velocity times time. That is your key. That is what you have to internalize and continue to use. Distance is equal to speed times time, constant velocity. And of course, you can write that in the other two ways. The velocity is equal to the distance over the time. The time is equal to the distance over the velocity. You can write that in any way you like. That's why we were looking at those literal formulas before, so that we're comfortable in turning this little simple three-term equation around in any way that's convenient for us, depending upon what is the known and what is the unknown. So let t equal the time that we have traveled. Isn't it true that the first car will go 35t, speed times time? Isn't it true that the second car will go 50t, because t is how much time he's traveled? So they've traveled 35t and 50t. They are, therefore, this sum, that's how far away they are. We're told that that's 255. Okay? And that's the equation. That's turning it into the language of algebra. The rest we can now solve for t, how much time that takes to get out to a distance of 255. We simply can collect like terms and divide by 85 and get, it takes 3 hours for them to be separated at 255. And you can check that by multiplying 35 by 3, 50 by 3, adding them together, and in fact, you will get 255. Question about this one. Okay, we'll go on to the next one, a geometry problem. The length of a rectangle is 3 times the width. The perimeter is 96. Find the length and the width. Let W be the width. Therefore, we're told immediately that 3W is the length. The length is 3 times the width. So the length is 3W. We know the perimeter is twice the width plus the length. One of our formulas from those boxes. The perimeter is equal to twice the width plus the length. And there's our formula. Okay, the rest is math. Multiplying through the bracket, isolating, solving for W. The width is 12. We're told that the length is 3 times the width. so the length must be 36. Question. An age problem. Mary is twice as old as John. The sum of their ages 7 years ago, again, I know, silly. The sum of their ages 7 years ago was 31. How old are they? Okay, here is the more sophisticated way of doing this. Here is we want to work with two different variables and combine them up. This is something that I think I do want to try to review carefully. We don't have immediately, it's not immediately obvious when you read the English that you can really write Mary's age in terms of John's or John's age in terms of Mary. So best to think of them as two separate variables and try to translate what's given here as individual equations, and then see if we can deal with those individual equations algebraically. So if we let J be John's age, oh, I'm sorry, I'm jumping ahead. This is where we can immediately write down Mary's age. I'm anticipating where I want to go in later problems. So Mary is twice as old as John. So if John's age is J, then clearly Mary's age is 2J. All right, we're not there yet, but we are told that 7 years ago, J minus 7 and 2J minus 7, the two separate ages, they add up to 31. Okay. And we have an equation where we can collect like terms and solve. For John's age is 15 and Mary is twice that, which would be 30. Question. Another motion problem, two people start from the same place at the same time and travel in opposite directions. One is moving 20 miles per hour faster than the other, and they're 600 miles apart after 5 hours. Remember, distance is equal to speed times time. What is the speed of each? Well, let V be the speed of A, the slower, and we're told that the other guy is moving 20 miles per hour faster. So the speed of B would be V plus 20. We get that immediately from the fact that he's moving 20 miles per hour faster. There are our two speeds. They've traveled for 5 hours. So in 5 hours, A has gone 5V, and B has gone 5 times his speed, V plus 20. That's time times velocity. Time is 5. Times speed. Times speed. Those are the two distances. We're told those distances together make up 600 miles. And so there's our equation. Simplifying and solving. The slow velocity is 50 and the other guy is 20 miles per hour faster, would be 70. Question. Okay. Here's where I wanted to be, these last three. Here we will have two independent relationships. It's not clear from these two sentences that one is, 3 times the other or 4 times the other. They're just two very simple sentences. The sum of two numbers is 13 and their difference is 5. I think it's very natural to say, well, let's call the first number X and the second number Y. And then let's translate these sentences above in terms of X and Y. Here we're dealing with two variables, two unknowns for the first time. So the two equations are straightforward enough. X plus Y is 13 and X minus Y is 5. Okay, that's pretty straightforward translation. Notice I have X as the larger number. That's why I'm allowed to subtract X minus Y and get positive 5, because I have designated X as the largest number. Very important to, very much specify as best you can, as clearly as you can, just what these variables mean. Otherwise, your translation will break down. So how do we deal with two equations and two unknowns? You may remember, it's called the substitution method. I take one of the equations, doesn't matter which one. I've chosen this one as actually simpler to work with for my purposes, and I solve that equation for one of the unknowns. Again, why we work with literal equations, so that we can isolate any term that we like. So here I can isolate and solve for x by adding a y to both sides. And now that I have x in terms of y, I can take the second equation that I haven't used yet, the sum equation, x plus y is equal to 13, and use for x 5 plus y. So here I have my second equation, x plus y is equal to 13, and I use for x what x is equal to from the first equation, 5 plus y. And I have an equation only in y, simple to solve. Okay. Collecting like terms and solving for y, y is 4, x is y plus 5, is one of my equations showed, so y must be 13. And indeed, their sum is 13 and their difference is 5. An age problem. The sum of John and Mary's age is 24, and in 4 years, Mary will be 3 times older as John. In 4 years, Mary will be 3 times as old as John. This is the one I thought I was talking about. Let J be John's age and M be Mary's age. The first equation is straightforward. J plus M is 64. The second one, in 4 years, Mary will be 3 times as old as John. Well, Mary will be M plus 4. John will be J plus 4. And we're told that Mary's at that time, M plus 4, will be 3 times older than what John will be then. And there are 2 equations. Again, the same trick, I take one equation, simpler one. I choose to solve for Mary, could just as well solve for John. I solve for Mary and take that second equation, which I haven't used yet, M plus 4 is equal to 3J plus 4, 3 times J plus 4, and I substitute for M, 64 minus J. And this is an equation that only has J's in it, and if I'm careful, I should be able to solve for J, J being 14, and we're told that Mary is 64 minus J, which would make her 50. And I think the last one. By traveling at one speed for 2 hours and another speed for 7 hours, the distance covered by these 2 travelers would be 258 miles. I'm sorry, for one traveler, the distance he would cover would be 258 miles. If the first speed is picked up by 10 miles per hour during those 2 hours, and the second speed is twice as fast as that first speed during those 7 hours, then the new distance covered will be 488. What were the original speeds? Yeah, it's an exercise, guys. It is a crazy question, but it makes you tease through and try to translate this into algebra. So let V and U be the 2 speeds. This is a much simpler way to approach it than trying to figure out a relationship immediately between V and U. It's too complicated. You have to read this thing 3 times to understand what it's saying. And I'm very serious about that. You don't get these problems by just reading them the first time, not stuff like this, okay? Never mind the problems that we'll be getting to in the real world. So we have 2 different speeds. Now we can go back and read the question and try to tease through what these sentences are saying. The first distances is 2 times V and 7 plus U, because those are the hours that they spent. It's a speed times a time, a speed times a time. In the second situation, I picked up one speed by 10, same time as 2. I doubled the other speed to get to 2V, same time by 7. Now that distance would be 48. And now it's the same deal. I go ahead and take one of the equations. Neither one is a bargain, but I take one equation and solve for U. Yeah, it's a mess, but you can deal with it. It's okay. We'll take the second equation and throw that mess in for U. Just be careful, not as bad as it looks. Look at that, you got 14 over 7. It's only 14 over 7. Simplifies to just a 2 outside, and following your nose, we'll get V is equal to 24. And going back to the equation that isolated U, calculated to be 30. Okay, so that's where we are. Jenny, any questions accumulated as I ran through that?
Nothing in the chat right now, no.
Okay, anybody want to
first one.
open up and unmute themselves and throw out a question?
Yes, hi, Peter.
Hi,
In the word problems you gave us earlier this week, the second one, I think you gave an answer of 18.
yes,
And
I did.
I think there was a second answer, which would be 42.
Oh, for the two numbers.
Yeah,
Oh, no, wait, that question is the difference between 15 and 1/2 of a number is 6. So I am only looking for one number.
yeah. Well, I found two numbers though that solve the equation, I
Oh,
think.
you said there are two solutions to the equation.
That's right.
18 and what's the other solution?
42.
42. Okay. Let me take a look at that. I did not think I had any quadratics in here, which would give two solutions. The difference between 15 and 42 and one half of 42 is 21 would be, that's right. Okay, 42 is another solution. Let me take a look at that. I thought I tried to not do those in the early part. Okay, thank you. Good catch. I'll address that on the Tuesday email.
Okay.
Any other questions? All right, so I've left you with a ton of problems. Hopefully, looking at the ones that we went through together help those who were. So take a look at these problems. I'll give you a ton more in the next presentation on Tuesday, dealing with fractions and factoring. And that pretty much will load up our algebra. And then you can see just where you are. Do you want to continue with this? Can you handle this? Is this really too much? Is this okay? Do you want a second class? So take a look at my Tuesday solutions. I will do a better job being more careful in giving you my solutions. Take a look at the new questions that I throw at you. Again, the explanations will be in the presentation, but it'll be stuff that, again, you knew long ago, factoring and handling equations with fractions. See where you stand with all this stuff, and we'll kind of assess where we are next Thursday as to just how we want to proceed. Okay, guys, have a good week. See you next week.
Peter,
Yes.
Jenny here. There was one more comment in the chat if you'd like to read that
Oh,
before you
please,
close off.
Please.
Okay. Well, in the past, I always struggled with conceptualizing word problems, so wondering if we can work through them a bit slower so they can be more fully digested.
Okay, certainly that's very legitimate for one person to say. If 5 or 6 people have the same thought, then there's where I would like to do a separate class where we could do this more slowly, because I have a feeling that maybe half of you don't need that extra time. Here's where I could be wrong, okay? So that's where let's wait until next Thursday. Maybe even if I could ask for you guys to be ready on Thursday to give me a show of hands as to where we think we stand to proceed, okay? It's a very legitimate point, and I'm sure it's shared by more than just one person. The question is how many people and how to address that issue. Okay, guys, again, thanks for your attention, and see you next week.